Welcome to True Projects. In this video, we are going to explain the project Solar Cell Surface Defect Detection based on optimized YOLOv5. Introduction. This project aims to enhance solar cell defect detection accuracy using an optimized YOLOv5 algorithm. The primary objective is to develop a more precise and efficient method for identifying defects in solar cell devices. Accurate detection of defects in solar cell devices is crucial to ensure the reliability and efficiency of solar power generation. Traditional methods for solar cell defect detection have limitations, including low accuracy in identifying defects. These techniques may not provide the level of precision required to guarantee the quality of solar cell devices. So, to overcome the limitations of traditional methods, this project incorporates several enhancements. It utilizes image processing techniques such as mosaic, mix-up, HSV transform, scaling, and flipping to improve image clarity. Additionally, the YOLOv5 algorithm is modified with a channel attention, that is CA model, to enhance feature extraction and defect localization, significantly improving detection accuracy. And this project benefits the solar industry by providing a more reliable and accurate method for detecting defects in solar cell devices. It ensures that solar cells are deployed with higher quality standards, ultimately contributing to more efficient solar power generation and long-term cost savings for both manufacturers and consumers. Objective of the project. So, our main goal is to create a top-notch system for spotting defects in solar cells. We are using YOLOv5, a powerful tool in computer vision, to ensure precise defect detection. Clear images are crucial for accurate defect identification. We are using 4 image enhancement techniques: mosaic, mix-up, HSV transformation, scaling, and flipping to make our pictures clearer and help us detect solar cell defects more effectively. And we are introducing a channel attention CA model to extract important features from images and classify different types of defects. Additionally, we are replacing the detection head in the YOLOv5 model to boost accuracy without slowing down the process. And to validate our optimized YOLOv5 system, we are conducting a comprehensive comparison with the widely used faster RCNN algorithm. We are using various performance metrics like accuracy, precision, recall, F-score, confusion metrics to see how well the system performs in comparison. This helps us understand if the new approach is better suited for real-world applications. Requirements needed to execute this project are software requirements: software of Anaconda, primary language of Python, front-end framework used is Flask, back-end framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8GB and above, hard disk of 25GB and above. Now we'll discuss the working modules of Law of Work. The first step is importing required packages. In this step, we import the necessary Python libraries and packages that are essential for data processing and machine learning. This includes libraries like NumPy, OpenCV, Keras, etc. The second step is exploring the dataset. So, in this step, we examine the dataset that contains images of solar cells and associated labels. Understanding the dataset structure, size, and content is crucial for subsequent data pre-processing and model training. The third step is data pre-processing. So this phase involves preparing the dataset for machine learning. Data pre-processing steps include resizing images, converting color spaces, that is HSV transformation, and augmenting the data by flipping images. These actions enhance the data quality and facilitate more accurate model training. And in the next step, we categorize the solar cell images into 2 classes, mono and poly, based on their associated labels. This step is essential to create a supervised learning dataset for the machine learning models. The next step is train and test split. So in this step, we divide the dataset into training and testing subsets. The training dataset is used to train machine learning models, while the testing dataset helps evaluate their performance. The next step is train and evaluate machine learning models. So here, we train and evaluate machine learning models such as faster RCNN YOLOv5 with CA attention using the training dataset. The evaluation assesses the model's performance in terms of accuracy, precision, recall, F-score, and mean average precision. And as an extension, we build the YOLOv6 algorithm, which is an advanced version of YOLOv5. This model enhances solar defect detection capabilities further. And the next step is performance comparison. So here we compare and analyze the performance of all the machine learning models, including faster RCNN YOLOv5 with CA attention and YOLOv6. We visualize the performance using bar graphs and summary tables. And the project extends beyond model development by creating a user interface using the Flask framework. This interface facilitates user interaction, authentication, and input submission for detection. And the next step is Flask framework with SQLite for sign up and sign in. In this step, we integrate user registration and login functionalities into the Flask framework. Users can sign up by providing their information, and subsequently they can securely log in using their credentials. This enhances system security and allows for personalized user experiences. So after logging in, users can provide input, typically in the form of uploading a solar cell image that they want to analyze for defects. The input image is pre-processed, similar to how we pre-processed images in the dataset. This ensures that the input is in the appropriate format for the machine learning models. And we use the pre-trained machine learning models to make predictions on the pre-processed input image. This step involves defect detection and classifying defects as mono or poly. And the final prediction and analysis results are displayed to the user through the front end. Users can see the predicted defect class and associated probabilities. So these are the algorithms built. The first one is faster RCNN. So faster RCNN is a renowned object detection algorithm that integrates deep learning with region proposal networks, allowing for precise identification of objects within images by providing class labels and bounding box coordinates. In this project, faster RCNN served as a benchmark for evaluating the performance of other algorithms including YOLOv5 and YOLOv6 in the context of solar cell defect detection. The second algorithm built is YOLOv5. So YOLOv5 is a real-time object detection algorithm that divides images into a grid, enabling efficient prediction of bounding boxes and class labels for objects within each grid cell. In this project, YOLOv5 took center stage, undergoing optimization and enhancement through image pre-processing techniques and the incorporation of the channel attention, that is CA model, to boost its accuracy in detecting defects on solar cell surfaces. And the last algorithm built is YOLOv6. So YOLOv6 is an extension of the YOLO algorithm family, renowned for real-time object detection. Building upon the principles of YOLOv5, YOLOv6 introduces architectural and training improvements to achieve even higher accuracy. It was included in the project as an extension to assess whether it could outperform YOLOv5 in terms of prediction accuracy for defect detection in solar cells. So this is the comparison graph. In this graph, on x-axis I have the algorithm names, and on y-axis I have performance metrics, accuracy, F-score, precision, and recall. So accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And F-score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So we can see extension YOLOv6 is doing well in all the performance metrics when compared to other models in this particular project. Execution. So to execute this project, first we need to open the code folder which contains the project source code files. So this is the dataset folder in which I have solar cell images and their associated labels in this file. So we will train the machine learning models using this data. And this is model folder. This folder consists of pickle, numpy and .hdf5 files which contains algorithm information. These files will be loaded into the project during runtime. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc. which represent different pages of the website. And this is test images folder in which I have these images on which we will make detections. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database and generating dynamic content to be rendered in the HTML pages. And this is notebook.ipynb file. This Jupyter Notebook file contains combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. Now copy the path of the code folder from the address bar of the file explorer. I'm copying it. And open Anaconda prompt. Use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. So after running the app.py file, the Flask framework will host the application locally at the default address, local host and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a register link, click on it. So if you are new users, we have to register first. Fill in all these details and click on submit button to register. And if you already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password. And click on submit button. So it has redirected us to the solar defect detection page, and here we have to upload the solar cell image. Click on choose file button. So from test images folder, I'm selecting the first image and click on open. So the image has been loaded. Now click on upload button. So in the red color text we can see the prediction. So the detection defect labeled as mono, and we can see defect probability. The probability represents how certain the model is about this classification. Click on back. Click on choose file button again. This time we'll upload 6th image and click on open. So the image has been loaded. Now click on upload button. So in the red color text we can see the detection. So the detected defect is labeled as poly, and we can see defect probability. Click on back and now click on logout button. So the conclusion here is this project optimizes YOLOv5 for precise solar cell defect detection, significantly improving accuracy. Image enhancements like mosaic, mix-up, HSV transform, scaling and flipping boost clarity for better defect identification. The introduction of a channel attention, that is CA model, and replacement of YOLOv5's detection head improve feature extraction and defect classification without compromising model convergence speed. Comprehensive comparative evaluations bet the optimized YOLOv5 against the established faster RCNN. Results highlight its superior performance in accuracy, precision, recall, F-score and confusion matrices. And as an extension, the project explores the YOLOv6 algorithm which achieves higher prediction accuracy. It offers a robust solution for detecting defects in solar cells and improves performance. And by implementing these enhancements and extensions, the project delivers a powerful solution for solar cell defect detection, promising more reliable, accurate, and efficient outcomes in quality control processes.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.